Hey everyone, welcome back. In the last video, we solved problems based on print factors. Okay, so in that question, we were printing all the factors of a number, right? We are 18 and we are printing all the factors of 18, and we had seen two methods in this problem. First one was with the time complexity of n, right? In which we were iterating from 1 to n and checking if the remainder is 0 or not. Similarly, then we optimized the solution and our time complexity becomes root n. Okay, and this is the condition which is making sure that there is no duplicates, right? Because in this type of cases there is chance of getting duplicate factors, so to avoid that we have to use this condition. Okay, so now today we are going to start with the new problem, which is prime number. So everyone must have learned in 9th, 10th, 11th, 12th or in the BTech what is a prime number. So today we are going to write a code to check if a number is prime or not. Okay, so first of all, what is a prime number? So prime number is a number that has exactly two factors. What I'm saying, let's say you have 2, right? We know 2 is a prime number, and what are the factors of the 2? 1, 2. Then let's take 3 factors of 3, 1, 3. Factors of 4, 1, 2 and 4 itself. Then factor of 5, 1, 5. Factor of 6, 1, 2, 3. Then 6. Here you can see the number which are primes only have two factors. Okay, so our definition is that a number is a prime number if that number has exactly two factors. Okay, so remember this definition. Based on this definition we are going to write our code. Okay, so here we are talking about factors, right? So in the last video we were printing factors. Can we use this code to find our prime number, right? Because in prime number we need two factors, and remember it is exactly two factors, no less than 2, not greater than 2, exactly two factors. Okay, so let's come to the code. So first we will write a code with the time complexity of n. Okay, so let's write here prime number. First we will take a number, then we will write a loop. Okay, and let's take one more variable which is count, and if a number is divisible by, then we can say it is a factor, and if it is a factor we can count plus plus. Then here we will write count equals to 2, then we can say it is a prime, else not prime. So what's happening here? Let's take a number 7. Okay, so we have I equals to 1. So here 7 modulo 1, it is 0. So 0 equals to 0, condition true. So our count becomes 1. Okay, then we have I equals to 2. Then we will check again 7 modulo 2. No, it is 1. 1 equals to 0. No, false. So our count will remain 1. Okay, now let's take I equals to 3. So is 7 divisible by 3? No. So our count is still 1. I equals to 4. 7 is not divisible by 4. Then I equals to 5. No. I equals to 6. No. I equals to 7. 7 modulo 7, 0 equals to 0. True. So our count will become 2. So after completing our loop, we will come outside the loop and we'll check the condition. Count equals to 2. Our count is 2. 2 equals to 2. True. We can print prime number. Also we know that 7 is a prime number, right? Now let's take another example. This time let's take 4. Okay, so 4 modulo I equals to 0 means 1. 0 equals to 0, condition true. So our count will become 1. I equals to 2. Okay, then 4 modulo 2 will 0. 0 equals to 0, condition true. So our count will increase. So here it will become 2. Then I equals to 3. 4 modulo 3, 1 equals to 0. No. So our count will remain 2. Then I equals to 4. 4 modulo 4, 0. 0 equals to 0, condition true. So our count will become 3. Now our count is 3. 3 equals to 2. No. So it will print not prime. So we know 4 is not a prime number. So basically we are still finding the factors, but this time we are counting number of factors, because prime number can only have two factors, and other than prime they can have any number of factors. So we are using this concept that prime can have only two factors. Okay, now let's talk about time complexity and space complexity. So the code is still same. So our time complexity is big of n, because we are going 1 to n, and space complexity will remain 1. Okay, so we can also improve this to the square root of n, right? Because we are still finding the factors. If we are still finding the factors, we can use our this method, right? We had a number, let's say 36, then we were taking 1. What should I multiply here? So it will become 36, then 2 into 18 36, then 3 into 12 36, 4 into 9 36, then 5 is not possible, then 6 into 6 36, then after that we will get a repeating number. So this one was I and this one was n divided by I. So we just have to go till the less than equals to root n. So we'll be able to find our factors. Let's write a code for this also. So first we will take n, let's declare our count, then we will write loop here I into I. Okay, I into I less than equals to n, because we are going till the root n, right? So it is like this, root n, then I can do a square of n, then I into I less than equals to n. Okay, so this is our condition here. Then I plus, then we will check n modulo I equals to 0, then we do a count plus plus. Also we will check n divided by I not equals to I, then we do again count plus plus. This if is inside this if. Okay, because we are checking for the same number. So here our time complexity will become big of root n, it is a square root n, and space complexity of big of 1. Okay, now let's write the code. So this is our code from previous question, so let's use this. Okay, let me remove, then we will write it again. So let's declare our count here, then we will run our loop from 1 to n I plus plus. Then here if n modulo I equals to 0, we can do a count plus plus. Then after this, if count equals to 2, then we can say prime number, else not a prime number. Okay, so now let's run this. So let's take 6, not a prime number, and let's run it again. Then 5, prime number. Okay, let's take 999, not a prime number. Okay, now let's write our code in the time complexity of root n. So what will be the changes here? It will become into I, right? Then here we will write another condition, if n divided by I not equals to I, then we do a count plus plus. Okay, so let's run it. Let's take 6 again, not a prime number. Let's take 21 or 11, prime number. Okay, so this is the code for checking a prime. Do remember, okay, because this is very important, and in the future most of the problem we are going to use prime number. Okay, now so let's move to next problem. If we are talking about prime numbers, so let's take another question, print prime factors. So question is, we have a number, let's say 18, and the factors are 1 2 3 6 9 and 18. These are the factors of number 18. Now the question is print prime factors. So what are the numbers which are prime? 1 is not a prime number, 2 is a prime, 3 is a prime, right? So you have to print only these numbers. You have to print only these numbers. So in this case we are using two concepts, first printing factors, also only printing prime factors. So let's write our code, because in this case we are using both concepts, so our loop will become nested. So first we will check if a number is factor or not, then we will check prime. Okay, so our loop will follows like, first we will check factor, then we check if that factor is prime or not. So we will write our loop for int I equals to 2, I less than and I plus plus. Okay, this time I am starting from the 2, because even if we check 1 is factor or not, it is not going to be a prime number, right? So why do we need to start from 1? You can start, but it is not a prime, so you don't have to check it for a factor also. So we will start our loop from 2, then we will check condition if that number is factor or not. If that number is factor, then inside this if we will write another condition, prime I, let's take is prime. Okay, so we can here print our I. Now what is this is prime? So basically is prime your this function. If you convert this code is prime function, right? So you will be able to find your prime factors. So how you are going to convert this code into the function? So first let's discuss time complexity. Okay, we will directly see in the code how we are going to use this code to convert to the function. Okay, so here our loop is running for an n time. Okay, then we are calling this function. If we are calling this function, so calling means we are going here for this function. In this function we are also running a loop which is going root n, right? If you do not use this function, you can directly write your code here. Okay, you can directly write your code here, so your time complexity will become big of n into root n, because these are nested loop, and the space complexity will remain big of 1. Okay, now let's write the code. You will be able to understand it. Okay, so I'm going to use same code. Let's remove it. Then let's create our loop for int I equals to 2, I less than equals to n, then I plus plus. Okay, we will check if that number is factor or not. Okay, after checking factor, we will check for the prime. So this is our code for the prime, so I can write here. Okay, so let's first see how we can do without using function. So we checked a number is factor, then we will run a code for checking a prime. So this is our code for the prime. Okay, so if after factor, after this loop, if our count is exactly 2, then we can print our I here, right? Because I is the prime factor. So let's run it. So let's take 18. Okay, there is some problem. Okay, there is problem because here we are using I based loop and here we are using I based. So we have to change it to the J. Okay, then here will be J, here also will be J. Let's run it. Let's take 18. Okay, again. Okay, so here it will be I, because I is our new number till which we are checking it is a prime or not. Now let's run it and let's take 18 again. So here you can see it is printing 2 and 3, because 2 and 3 are the only prime factors of the 18. Okay, so what we are doing, the first loop is running for checking a factor. Okay, so we have a number 18, we running a loop to find out the all factors of 18 if a number is factor, right? Because we are checking here condition, if it is a factor then it will goes inside this block, then our count becomes 0, right? Because let's say we are talking about 2, so start count is 0, then the loop will run 1 to root of 2, because we have to check for the 2 only, right? So we will go till the 2 itself, then we will check here prime. If 2 is a prime, then our count should be equals to 2, so we will print if the count equals to 2, so it will print 2 because it is a prime factor. Okay, so this is, you can write in this way or you can write while making a function. So for a function we will write int is prime, right? Here we are taking a number, let's say x, and let's pick this code from here and insert into that function. Okay, now here is not, this is x, so here should be x, here also x, right? Now here it is counting, so here we will do a return of count. Okay, we are calling this function which is counting the number of factors after checking it, so returning the count. So here we will write is prime, we are passing here I. If the function returning 2, then 2 equals to 2, right? Then it will print our prime factors. Let's write 18 again. Here you can see it is printing 2 3. Let's take 36 also, 2 3. Let's take 7. For a 7 there is only one prime factor, which is 7. Okay, 1 is not a prime number. And let's take another example, 365, then 5 and 73 are prime factors in this number. So our time complexity for this code is n root n. So can we improve the time complexity? Yes, we can improve the time complexity of this code, which is going to be 2 into root n into root n. So this is our constant, we can ignore it, so it should be root n into root n, which is better than this, right? Because one of the n we are converting to the root n. So let's directly see in the code. So we are still checking for the factors. So for the factors also, do we need to go to the n? No, right? We can go till the root n itself, right? Because we are still running a loop for checking a factor, so why do we need to go to the n? We can go to the root n. So we need to change this only, and our time complexity will become root n into root n. So let's run this. Let's take 56, 2 and 7. Let's take 2. Okay, folder 2, it is not printing anything. Okay, let's take one more example. 7, 4 prime number itself, it is not printing, because while we are taking 2, okay, so it is doing a root of 2, right? So we are sending our 2 to check it for a prime check, it checking a prime. Okay, the problem is this is correct, but while we are using here root n, we also have to consider this condition, right, where we were doing n divided by I not equals to I, and check if is prime. So the number we are getting by dividing, for this also we have to check prime. So here we will print cout equals to I. Here should be divide. Okay, let's run it, then we will see if there is any problem. Let's take 2. Okay, it's not working. Okay, here should be equals to 2. Let's see if it is working or not. No. So the changes I made here, we are checking for n divided by I, so we have to print n divided by I itself, right? And here we are starting our loop from 1 to n. Okay, because we are checking for the factors. If I was trying to start from the 2, it was not working, because if a number itself is a factor or prime, so it wasn't working for that case. In that case you have to start from the 1. Okay, so this is a code for printing prime factors. Okay, let's take another example. So let's take 5. So 5 has only its prime factor. Let's take 24. So 24 have 2 and 3 prime factors. Now the time complexity for this code is root n into root n, but there is a better time complexity n. Okay, so how we are going to write our code in a n time complexity? Okay, this time this n is still better than this one, right? Even we ignored 2, but 2 is still there, right, which is compared to greater than n itself. So here we have 2 root n 2 n, which is still greater than n, right? So it is a little bit improved from this time complexity. So let's see, we have number 24. If you do a LCM of this number, 2 1 2 2 6 2 3 3 1, if you observe here, 2 2 2 3, are these prime factors, right? These are the prime factors. Let's take another example. Let's take 5. This is a prime factor. Let's take 18. 2 9 3 3 3 1. These are prime factors. So instead of doing factors then checking a prime, we can directly do a LCM of the number. We will be able to find our prime factors. So how we are going to write our code? So our code start from 4 int I equals to 2, because we are starting from the 2. I less than n. Okay, for this we can do a I less than n. I am directly using root n, then I plus plus, then we have n modulo I equals to 0, then we can print our I. Okay, after this we have to write one more condition, not a condition but a loop, why we are running this loop. Okay, after this we have to write one more condition. Okay, we will see in the code what is the condition, because if I show you now you won't be able to understand it. So let's see how this code is working. So we are going till the root n, no problem, right? We are checking factors. Basically we have this number 24, we are starting from the 2, we are checking it is divisible. Yes, it is divisible. Then print 2, right? Print 2 because it is a prime factor. Then we are running this loop while n modulo I 0 0, means if we keep dividing it, we got a remainder 0. So let's divide it. It is 12. Then 2 comes again, right? We will check again, is 12 divisible by 2? Condition true. Then the while loop will continue until our n is divisible by that number. Now after this we will try to divide 3 with the 2. 1 equals to 0. No, false. The condition will become false. Then we will break out from this loop and our I will become here plus plus. So I will become here 3. So basically this loop is ignoring our duplicate values, or we can say skipping the duplicate values, right? Here you can see it is dividing again and again. First 24 divided by 2, 12, then 12 divided by 2, then 6, then 6 divided by 2, 3, then 3 divided by 2. No, the loop will stop. Okay, so this will work for every number. Let's take 9, 3, 3, 3, 1. So what it will do, it will check 9 modulo 3 true, then it will divide, it will become 3, then 3 modulo 3 condition true, then it will divide, it will become 1. So here our loop will stop because it is not equals to 0. Basically it is dividing the number until it is not divisible by that number anymore. Okay, so here time complexity I told you, n is for a large numbers, the numbers which are very large, and the approx time complexity for this is root n, right? Root n for this into log n, log n for this, because here we are dividing our n with the same number again and again. So our time complexity is root n log n. Okay, so this loop is for jumping directly to this number from here to here, because for these numbers we don't want to print 2 again and again, right? So let's run our code and see how it is working. We don't need this here, also we don't need this. So we will start our loop from 2, then we will print, right? After printing we will skip our duplicates. So n modulo I equals to 0, then n divided by I. So let's run our code. Let's take 24. It is printing 2. So here we are getting only 2, so we should also get a 3. Okay, now let's try one more example. 36. So it is printing me 2, 3. It is correct, but in this case it is not printing. The problem is that our loop is running till the root n, so it is not including our last value. After running a loop we have to write a condition, and if it is not equals to 1, then we will print n itself. Let's run it, then I will show you how it is working. 24, here you see 23. So let's come to our code here. So let's take an example of 23 here. Why do we need to write this condition? So we have 24, initially I is 2, so 24 modulo 2, it is 0, then it will print our 2. So we printed our 2. Now the while loop comes, right? So it will skip ahead till here. Now I becomes 3. Now what is the square root of 24? It is around 4.89. Okay, 4.89, and our I value is 3. I is 3. So here we are taking I into I less than equals to root 24, which is 9 less than equals to 4.89, which is false. So it is not running our loop for the condition of 3. So at the end what is remaining? At the end what is remaining? N equals to 3. So we can say the last prime factor is stored in our n itself. So we are writing here condition as long as our n is not 1, means you can write n greater than 1, means any n it is a prime, so we can directly print it here. So in the 24 what's happening? It is only printing 2 because we are not writing this condition, and n is storing 3. So we are at the end checking if our n is not 1, then we can print our n itself because it is containing prime factors. For the case of 36 it was working, right? It was printing 2 or 3. It was working correctly because 36 we will do a 2 divided by 18, 9, then I will become 3. So 3 into 3 it is 9, which is less than equals to 9. 3 comes here, then 3, then here 1. So here you can see our n becomes 1 in this case. In this case our n becomes 1, and 2 and 3 already printed. So this condition will not run for 36 because our prime factors already got printed here. Okay, so to avoid this condition you have to write this condition, which will make sure if there is a prime factor still stored in the number n, which can be printed at the end. So try to dry run it yourself on different numbers, so it will be easier to understand, right? So that's it for today. Thank you everyone, have a nice day.